Okay, so now let's jump into the next electrophilic aromatic substitution reaction. It's the Friedel-Crafts acylation reaction. So again, let's do an overview. And then after we do the overview, we'll look at the mechanism for this reaction. So this sounds a lot like the Friedel-Crafts alkylation reaction, but it's important to remember an alkyl group is an alkane. An acyl group is a carbonyl group. So in this reaction, what you're going to do is you're going to react an acid halide. So in this case, this whole group is called an acid halide. So it's kind of like a ketone where one of the carbons is swapped out for a halogen. All right, so we've got that acid halide. We still need an acid catalyst like aluminum trichloride. And when we're done, what we're able to do is we're able to install that carbonyl group directly onto the ring system. Specifically, what we're able to make are ketones. So the ketone that we make can then be used to react with a Grignard reagent, or it can be reduced to an alcohol. There's a variety of different things we can do with that ketone. Specifically, this whole group is called an acyl group, hence the name Friedel-Crafts acylation. All right, so let's go ahead and look at the mechanism for this reaction. The mechanism looks a lot like the previous reaction we looked at, where we have this acid halide, and the halogen has lone pairs, and those lone pairs could be donated to the empty p orbital on aluminum trichloride. So we've got this p orbital hanging out here. This chlorine, let me change colors, it's going to just dump its electron density into that p orbital. All right, so we're almost there. We now have this chlorine coordinated to that aluminum. And that gives the aluminum a negative charge and the chlorine a positive charge. Just like we saw before, this leads to a really unstable chlorine. So what will happen next is we'll just kick that chlorine off entirely. Okay, so now we need to figure out what the next set of intermediates looks like. All right, it looks a little bit weird. And what I'm going to do is I'm going to actually draw the carbon, specifically this carbon right here, right down here, so we don't lose track of it. We still have that double bond to oxygen. And that carbon, after it loses that chlorine, will have a positive charge. All right. This oxygen still has its lone pairs. We could draw those in if we want. And this is called an acylium ion. Interestingly, though, this isn't the major resonance contributor. So let's think about this. We've got a lone pair here that we can dump down. So really, the major resonance contributor is going to be the resonance structure where we have a triple bond between the carbon and oxygen, and the oxygen has a positive charge. Now, a lot of students will ask, why in the heck would this be the major contributor when oxygen has the positive charge? Well, if you remember back to first term, we said that the most important thing in a resonance structure, meaning the major contributor, is that every single atom has full octets. The structure over here where carbon has a positive charge, that carbon doesn't have full octets, where this structure right here does. So that's actually going to be the major contributor. All right, you can show it either way. I just wanted to emphasize that point. And what we'll do next is we'll have this react with our aromatic ring. Okay, so I'm going to draw benzene as my aromatic ring. That's going to be our weak nucleophile, and it's going to attack our electrophile, which in this case is going to be the carbon on the acylium ion. Does it matter which structure you use? Not really, but I'm going to choose the major contributor, and we'll kick up electrons to that oxygen. All right, so we'll make our intermediate, but we're not quite done yet. Our intermediate has that carbonyl group installed. We still have these two remaining pi bonds, and we've got our positive charge there. So that's our sigma complex. But we also have this aluminum complex floating around in solution, where the aluminum has a negative charge. And this chlorine can act as a weak base, can grab this proton, and it can restore aromaticity to the system. Thereby giving us our acylated product and regenerating our aluminum trichloride along with our hydrochloric acid byproduct. So it's a pretty nice reaction, pretty straightforward to carry out. And then the other nice benefit to this is in the acylation reaction, we're installing this whole group right here. And this is an electron withdrawing group. And it's important to remember it's electron withdrawing because we have a resonance structure where we can pull electron density out of the ring. And therefore, the electron withdrawing group prevents this reaction from over-acylating. That was one of the big pitfalls we saw with the alkylation reaction. In the alkylation reaction, we weren't installing an electron withdrawing group, but rather we were installing an electron donating group. That led to the problem of over-alkylation. All right, I did want to show you one other trick that you can do, specifically after you install your acyl group. And this is called the Clemmensen reduction reaction. And I'll show you how we can get around this pitfall that we saw in the previous video. So in the previous video, I said if you use a reagent like 1-chloropropane and aluminum trichloride, most students are at some point tempted to draw this product. However, this is only made at about 35%. The main product, if you recall, is isopropylbenzene due to the carbocation rearrangement that will occur after that carbocation is initially formed. So this would be the major product. This workaround that I'm going to talk about is called the Clemmensen reduction. And so what you can do if you really want this compound is you can first do a Clemmensen reduction. So let's figure out what that would look like. Well, we know that we need 1, 2, 3 carbons. So our reagent that we're installing must also have 3 carbons. So I'll do this, 1, 2, 3. But with the acylation reaction, we need that CO double bond there. So we're going to put that in. And then aluminum trichloride. And by doing that, we can make a ketone that again has 1, 2, 3 carbons like that. All right, we're not quite there yet though. All right, in order to get rid of that CO double bond, we need to use the Clemmensen reduction conditions, which is a zinc amalgam. And an amalgam means that it's zinc that's combined with mercury. So it's a zinc-mercury amalgam with concentrated hydrochloric acid. And when you do that, you can actually completely get rid of that double bond, and you can get your desired product that we're unable to get in high yields using the above reaction. The one downfall to this is that it requires strong acid. Meaning that this won't work if you've got some sort of acid-sensitive functional group in your starting material. Luckily, the starting material that we're working with, meaning this starting material right here, doesn't have any acid-sensitive functional groups, so we don't need to worry about it here. We'll actually cover a few different reactions later on this term that look remarkably similar, where you can get rid of the CO double bond, but under more mild conditions or under basic conditions. All right, so that's where we'll stop today. Good luck studying, and let me know if you have any questions.